just now we are going to our virtual congress again. Professor Dimitri Khoshtariya's presentation is going to be live. He's one of the participants of the APMAS Congress. He's from I.Javakhisvili, Tbilisi State University from Georgia. The title is the self-assembled atomically defined bilayered silver L-crystalline copper junction capable of coherent multiple electron hole exchange. Professor, do you hear me? Professor Khoshtariya, do you hear me?
Yes, yes, thank you.
Yes. And also we can hear you clearly. Welcome again.
I try now to share my presentation on screen. Yeah.
Yes.
Okay.
And also, I would like to remind that this virtual congress is recording. Yes.
Is it okay?
Yes, we can see your screen.
Yes, okay. I now increased full screen. Yeah, okay.
Okay, no problem. If
Thank
you are
you.
ready,
Thank you.
we can start.
Yes, thank you. Hello to everybody. So I'm representing here I.Javakhisvili, Tbilisi State University of Georgia, Tbilisi, and also Beritashvili Center for Experimental Biomedicine, Tbilisi, Georgia again. So it will be my pleasure to present my talk about the self-assembled, atomically defined, bilayered gold, cysteine, cuprum, or copper ion junctions capable of coherent multiple electron hole exchange. So I express my thanks to funding organizations and also co-authors, certainly, to Dr. Dolidze, Dr. Nioradze, PhD student Laliashvili, and to our foreign collaborator, Rudi Van Eldik from Germany. Well, let me to go to first slide where I show some pictures about systems we are studying currently and about the equipment, which is main experimental equipment in our studies. And so on the right hand, one can see that there are depicted complex systems, quasi two-dimensional systems, complex systems, hybrid systems in which we use gold platforms, conducting platforms, as it is shown here in a very general picture here, and some organic components, organic like alkantiols, and some examples were shown in the previous talk, by the way, by Professor Banuoral. These organic components usually have some terminal groups which are capable of absorbing redox active species like proteins, for example, which is shown on the right hand here, extreme right. And this is another presentation of some typical system. But also it is possible to use this self-assembled monolayer films with more difficult and complicated functions, which can, for example, absorb metal ions directly, and these metal ions, which are actually redox active species, they can act as active elements of the system, of these nano devices. And so, and we try to even design some new systems or modify some well-known systems such to obtain some new properties for these systems, which could be applicable in applied fields such are energy storage, for example, but such batteries, for example, electronics, and so on. So also these systems have very important fundamental role, because we can study with our methodology elementary mechanisms, physical mechanisms of electron exchange in these systems on the fundamental level. And the equipment we study in this and other work is just standard potentiostat, galvanostat, voltammetric technique, which is well elaborated, generally speaking, and the 3 electrode configuration for this method, in which the working electrode is just the electrode, modified electrode, which I described above. So in this particular study, we apply as an organic element, this is a bioorganic element, a well-known compound, which is amino acid, actually, which is L-cysteine. And so this system with gold electrodes coated by L-cysteine is well known for a long time, but we try to manipulate with this system to obtain some new function. So to change something, this is well known that it's possible. It's possible to change the state of the two-dimensional layer by some manipulations. It's well-known cases. These are well-known cases when they may drastically change their function, their behavior, and so that's it's possible potentially in principle to obtain new features, new properties for these systems, which could be important for above mentioned applied aspects. And there is also very well elaborated theoretical basis for this method, because from the signal, for example, cyclic voltammetric signal, one can extract a lot of information, static information about the static features of the system, for example, the surface coverage, for example, or dynamic features such as, for example, number of electrons, active electrons transferred per one single elementary act. Just I mentioned that normally this is 1 electrode and maximum 2 electrons are studied and known for the scientific community, but theoretically, in principle, any number of electrons could participate. But this is restricted by several physical reasons, intrinsic physical reasons. So we also apply some post-Marcus physical theories and their extensions to try to go beyond these traditional approach and traditional already established models, so to try to find new possibilities for this kind of systems. And indeed, for the cysteine system, so I mean gold electrode coated by cysteine, I mean full surface coverage, and then this is saturated by copper ions, copper 2 ions, also under saturating conditions. So we under some manipulating conditions, we observed very interesting, and for the first time in real time, some transformation, possibly the phase transformation, which was manifested through the dramatic change of the signal, voltammetric signal, from the broad signal. Here is shown in blue color, broad signal again. So characteristic of a single electron exchange, and two very sharp signal, and which grew at the cost of this broad signal. So appearance of this new signal took place at the cost of the decrease of the intensity of the previous signal. So it means that there is some substitution of the mechanism, and according to the Laviron theory and post-Laviron models, Thinner signal should correspond to the participation of multi-electron case. So it means that more than a single electron is involved in the exchange per single elementary act. And so, but also the preservation of the intensity, oral intensity, indicates that the whole number of active copper ions is not changing. So in the coverage, there is the same copper. There are no copper added or released. So, and all the copper goes to some new state, and finally what is formed, it is what we have, it is this very sharp, unusual signals formed in the finally, and so these are rather stable signals already, and so it could be so used for several hours or even days. And measured, and so they are stable. And so, and then we applied this above mentioned so theoretical basis, so to estimate some parameters for this. For example, as I mentioned, the surface coverage and so other parameters. But what is most important that we directly see that. So if we can see the upper four lines, so number of electrons transferred per elementary act, as I mentioned, in the pre-transition state, it's approached unity. So this is probably normal, of course, normal one single electron transfer process, which was known before, but what is shown in the following four lines, number of electrons may vary, and so it is much more than unity. So in average, but it varies also. It varies in time, and so until the signal is established. When signal is established, then it is more or less constant. So so we can see that formally this corresponds to many electron transfer, which amounts to 6, 8, or even 16 in some cases. So you can see that initially the peaks are very sharp, but then the established peaks are more have also very sharp shape. So. And so then we applied also, in addition to experimental work, and I have to mention that we have performed systematic work, experimental work, which results are not shown here because just for 15, even 20-minute presentation, I would like to focus on physical aspects, main aspects of this work, and experimental CV curves are more or less similar to each other. So, and I have to mention that we applied computer modeling programs to create some idea what could be the physical nature of this transformation into the dimensional system, which could bring to the many electron transfer event. And so, and in the left-hand panel, which depicts the panoramic and top views on this studied system, where one can see that these dark gray balls are depict gold atoms, and so other colors are usual definition. Just I mentioned pink or plum. I think plum is copper here, and other are sulfur and carbon, and so blue is nitrogen. So, but in our model, and it is based on all all the series of our experimental work and their analysis, and also cross-analysis by invoking all the modern theoretical conjectures about the bilayered junctions. So it's important that all the knowledge is somehow incorporated here, but so I cannot follow these logical chains in this brief communication. But our paper devoted to this subject, a full paper, it's now will be published soon in in Nano Futures journal by Institute of Physics of the United Kingdom. So there will be all details will be presented there, and in the left hand panel we see that there is coordination of copper ions mostly by the carboxyl groups of the same component, which is cysteine, as I mentioned, but this is preferably electrostatic coordination. So it means that probably here the first coordination sphere is not strictly planar, and they should be somehow situated non-parallel with each other. So it is, but because electrostatical requirements are here the main requirements. This is the same given here in balls and stick model just to compare. And in the right hand side, we present the model which can explain more or less. We think convincingly how the coherence can appear in the system, and how the electrons can then move coherently and in collective manner. So it means that there is some kind of strong interaction, which by analogy of other systems, most well-studied system is, by the way, cuprate superconductors, high temperature conductors, which contain these layers of cuprates, which are situated strictly parallel, and between them is well known that interplay between superconducting features, at least not strictly at high temperature, but very close to high temperature, and so also this is connected with some interaction which is antiferromagnetic. So we consider that here in our system some kind of this tetragonal planar complexes are formed with around the copper, in which strong electronic delocalization or hole delocalization, because in the initial state when we form the system, these are system of holes, but we see that it is exchanged, so the holes are then filled by electrons as a result of multi-electron exchange, multi-electron hole exchange. So holes are replaced by electrons which occupy same orbitals as we propose, and they are still delocalized, and so it means that they form this whole united system, at least with several planar domains, which we call, and this is it is called in literature plaquettes, which are delocalized altogether, and so they may contain these kind of domains just which are equal, which represent the number of those electrons and holes which are exchanged, and we see this in experiment. So, but as I mentioned, this probably this system is in this case is not so stable to form the constant number of domains in this kind of subsystems. So this is fluctuating system, probably fluctuating system, which and fluctuations are such that they contain more or less increased number, but they are not constant actually during the whole observation of the system. And this was I presented here structural model, and so then we produced the energetic model, and this is last slide in this my presentation, that because this model, which is situated in the bottom part, in the lower part, it is different from single electron model, which is well known in other theoretical studies, when the electron exchange takes place between the Fermi level, upper Fermi level, variable and some empty orbitals of copper. But this is just I mentioned that the new subsystem, new quantum subsystem is formed in this kind of system thanks to very strong proximity effects and spin orbital interaction, interlayer spin orbital interactions, and this makes possible to form some kind of common condensed phase, some kind of some variation, some Bose-Einstein condensation. So when the whole these particles, electrons, are put together thanks to strong quantum forces, but this is not enough to form very stable system, but it is fluctuating system, but still it exists in some cases, maybe at lower temperature, because this all happens at room temperature. This explains instability and fluctuation nature. But at lower in temperature, what we plan to study, probably this will transform into a more stable system, which also can definitely exhibit two-dimensional superconductivity. So, in summary, I will give very short version of summary that we created new system thanks to some manipulations of well-known system, really new features, which probably is expressed, is probably so exhibited by multi-electron and hole exchange, and then by invoking models, well-known theoretical models for electron exchange, and in addition some spintronic models, because it is not single electron transfer probably. So we created models, structural model for such a system and many electron exchange, and also physical model for this exchange. So finally, so thanks for your attention, and special thanks to and best regards to the organizers of the APMAS 2020 from Tbilisi, Georgia. Thank you again for your attention.
Thank you, Professor, for your nice and very interesting presentation. Thank you so much.
Thank you.
And also, I want to ask to all of our participants, do you have any questions to Professor Khoshtariya? If you have any questions, you can write your questions to chat part, or if you want to ask your questions by yourself, please write the chat part about you have questions. After that, we can open your system voice and you can ask your questions by yourself. We can wait a few minutes. Yes, I think there is no question for now to Professor Khoshtariya. Thank you again, Professor. You are welcome. And also, I want to say and remind to all of our participants again, if you have any question after our virtual congress, you can send an email to Professor Khoshtariya about his presentation. Thank you again. Just now, we are going to a lunch break because Professor Sanas Tolendi's technical problem is not finished yet. If he is going to finish his technical problem, we are going to take his presentation end of the day. Just now we are going to a lunch break. About 1 p.m. About Istanbul, Turkey timeline, we are going to be here, and we are going to watch Professor Taras Kavanski's live presentation. He's from Biomatsen, and the name of his title is New Types of Amperometric Enzyme Biosensors based on Novel Polymer Matrices and Bio-nanocomposites for xenobiotics analysis in wastewater. Have a good lunch, and see you later about 1 hour later. See you later.